All right, guys, so this is lesson 1, real number system. Most of you or all of you should have seen this done in class where we filled in the notes. So I'm going to kind of move through it super quick. Remember, the real number system is any number on a number line. So I always revert back to elementary school when you had the number line on the front of the classroom, right? Those are your real numbers. They're the only numbers we talk about this year. And then we can kind of break them down, real numbers, into more specific groups. So we have natural numbers, which are counting numbers, starting with the number 1, okay, and so on. Then we kind of move on to whole numbers where we add that additional 0. So that's the only difference between a counting number and a whole number is now we add 0 to that set. And then we have integers, which now we're including their opposites. So it's all the whole numbers and now their opposites, which are negatives. And you can kind of see here that I kind of drew this little thing here to tell you that within these 3 groups of numbers, right, there are no decimals included. So we have no decimals in these 3 categories. But now decimals, they are numbers. So because decimals are numbers, now we can add them into this category of something being rational. And you heard me in class say, somebody's rational, they make sense, right there. It's relevant to what we're talking about. So if something is a rational number, it's a number that kind of makes sense to us. So, or we can predict, I should say. So really, by definition, a rational number is any number that we can write as a fraction, where my top number is an integer and my bottom number is an integer. So adding to this category now, we have repeating decimals. So for example, 1.77777, ... which just means it goes on forever, right? It's the same number over and over, or same numbers over and over. We add in fractions, right? We add in terminating decimals like 2.45, and we add in what we call perfect squares. So now this definition here, perfect squares under a square root, if I gave you the square root of 16, you could always take your calculator, right? And you could do second x squared, and you could type in 16 and revert it to become the answer, which is 4, which is a whole number, which again would be rational. So this is just a kind of summary of rational numbers here. Rational numbers now, remember, they include natural, whole, and integers. Okay, so what about all the other numbers, the crazy numbers out there that don't stop, they don't end, right? They don't repeat. Okay, those are called irrational numbers. And I don't know if anybody in here has ever been called irrational, but that just means you don't make sense. You're crazy. You're talking crazy. Like, stop being irrational, somebody might say. So irrational is kind of like that. It's a number that really doesn't make sense. It's not rational, right? We can't write it as a fraction. One of the most common numbers that, or terms that we've dealt with that is irrational is pi. So in middle school, you definitely have heard of pi. The other definition is, and these two go together, is a decimal that does not repeat, and it's a decimal that does not end. Okay, those we kind of use together. There's no repetition, right? They go on forever. And then the next one is a non-perfect square under square root. And now, just like when we dealt with the square root of 16, if I was to take this and put it in my calculator and do second x squared and do 45 and hit enter, I get this long decimal, 6.708203, right? That's what this is equal to. So I could add that in, right? That's the 6.708. I forgot what it was. 203, right? And 203, and we can just show that it goes on forever. So now by definition, this is irrational because it doesn't end or repeat. So now again, I kind of moved through that super fast because you already saw it in class as I taught it to you. This is just a good summary of basically what we just talked about. Real numbers are the overall name for everything. We can kind of break it up into 2 categories. We have rational numbers, right? And outside this bubble here, with rational numbers, we have decimals that terminate or end. We have repeating decimals, right? We have perfect squares. I'm trying to think of what else I had there. I think that, fractions. I'm sorry. I knew there was another one. Fractions. 3/10. Right? Those are all rational. And then we can kind of narrow it down and get smaller and smaller. And we talk about integers, which are our negatives and positives. Right? We talk about whole numbers, which now just start with 0, 1, 2, 3, 4, 5, and so on. And then we get more specific with counting numbers or natural numbers, which start with the number 1. Okay, so this is kind of just like this trickle down to the most specific type of numbers. And then over here we have our irrational numbers, right? That's pi, that's decimals that don't end or repeat, right? They just kind of go on forever. So this is kind of just a mapping of the two types of numbers. The biggest thing to understand here is that we need to be able to tell the difference between a rational number and an irrational number. So when we look below here, okay, we're starting we did some of these in class together. So you're classifying them as rational or irrational, and then you must be able to tell me why. So when we look at this first one, okay, we have 0.42424242. So we have this pattern or repetition where my 4-2, right, keeps repeating. So now as soon as I use that word repeating, we can type or state that this is a rational number because it's a repeating decimal. And it's super important to understand the why. Why is this number rational? Okay, so now if I bounce down to number 2, we have negative 3.312334, ... which means it's going on. So when I look at this number, I cannot state that it's repeating. I don't know what's coming next. I also know that it's not stopping because of that ... So if a decimal does not stop and it does not repeat, by definition, it would be irrational. And the reasoning would be decimal does not stop or repeat. Okay, working down here, number 3, I have 1.2 and then I have 8. So although I have this random 2 here, I have repetition of 8. So this 8 is my repeating factor here. What's going to come next would be another 8 if I wanted to keep this going. So because, again, it's repeating, by definition, it would be a rational number because it's a repeating decimal. Okay, back up to number 4 here. I have the square root of 35. So again, the way I always like to do this is if I would take this square root of 35 and I'm going to type it in my calculator. So I'm going to do second x squared and I'm going to type in 35. And I get 5.91607 and so on. And although it looks like it stops, it's only because your calculator does not or doesn't have the capability to show you more than 10 digits. So if it stops and it's kind of filling up that screen of all these different numbers, it's going on forever. So what we're going to do is we're going to put what this is equivalent to. So 5.91607. So this is equivalent to 5.91, and I already forgot, 91607. And we're going to do a ... to symbolize that it's going on forever. So again, by definition, a decimal that goes on forever and does not repeat would be irrational. Does not stop or repeat. And you're going to notice that your definitions or your reasons do get repetitive, and it will help you remember what each number would be. So number 5, 456,812. It's a really big number, but it's a whole number, right? There's no decimal here. I can count with that number, so it's also a counting number. This would also be an integer. So when you write your reasoning as to what this is, it's going to be rational because as soon as something is a whole number, a counting number, or an integer, it's automatically considered rational. So we can use that this is a whole number. And I'm just going to give you more. It could also be a counting number. It could be a good definition. Right? It could also be an integer. Okay? All of those definitions would work. You obviously would only have to pick one if it were on a test or a worksheet. Number 6 is negative 5.638. So notice I don't have a ... here, which means that the decimal stops or terminates. And again, by definition, a decimal that stops or terminates is rational. Okay, and my advice is when you're doing something like this, whether it be in class or at home, you kind of just look back at the notes. Looking back at your notes is a way to help you study it, a way to help you learn the material maybe a little bit better. So this is rational because it's a terminating decimal. You could also use the word ending or a decimal that stops. All three reasonings work perfectly. Okay, so now bouncing down to number 7 here, 3.14. 3.14 is a decimal that does not keep going. There's no ... So by definition, again, it's going to be rational because it's a decimal, and I'm going to kind of change up my explanation. Decimal that stops. That might be the most basic way to describe that. Here I have the square root of 4 over 81. Oh, and I'm bouncing over to here, but that's okay. So we have the square root of 4 over 81. So again, I'm going to use my calculator here. So I'm going to do the square root of 4. And then when we have that fraction, we can just use divide by 81 and hit enter. And we get 0.222222222222222. So that is a repeating decimal. Of course, though, we want to make sure that we write it down. Okay, we don't want to not write our answer because if we're going to use the reasoning that it's a repeating decimal, somewhere on my paper I have to have a decimal. So this is going to be rational because it's a repeating decimal. Okay, 22 over 7. Okay, 22 over 7 is a fraction with 2 integers, so that makes it rational. And by definition, it would be a fraction with 2 integers. You could also just say a fraction, that would work. 5.2727. So for this one, you'll notice that the 2, 7, both numbers repeat, right? And then we have a ... showing us that it does continue on. So again, this is rational because it's a repeating decimal. Okay, the next two, we can kind of use the same reasoning here. If you look at both of 9 and 13, they both contain pi. Anytime you see pi, we are always reverting to irrational. So this is irrational because it contains, and I'm going to show you how to put the pi symbol in. It contains pi. Oh, what did I just do? So the reasoning why this is irrational is because it contains pi. I'm going to kind of move it up to here. There we go. Okay, and again, 13 would be the exact same reasoning, right? It contains pi. Even though it's a fraction, it's not an integer up here. It's pi, the symbol, so it doesn't work. It's irrational. Oop, that didn't work. So I'm going to have to insert it again, but this is good practice with Kami, guys. You hit equation, and you would hit the pi symbol. So you're going to click on the screen to kind of insert it. And there's pi. Okay. So now we have the square root of 625. Again, what I would do for this is take my calculator. When I deal with the square roots, I always like to change them to decimals. So second x squared and 625. enter, and I get 25. 25 is a nice whole number. It's a nice counting number. It's an integer, so that would make this a rational number. And we are just going to write whole number. Again, you could write integer, you could write counting number. Either definition will work. Number 14, the square root of 3 over 5. So again, I need to use that calculator. Second, x squared, and 3 divided by 5. Hit enter. And if you notice now, we get this crazy decimal, right? 0.7745966692, that it just goes on forever. There's no repetition, right? So again, we're going to write down or type this decimal because we're going to use it in our definition. So it equals 0.77459. Dot, dot, dot. Okay, and again, but this is a decimal, like I said, that does not stop. It does not repeat, so it's irrational. And we're going to say the decimal does not stop or repeat. And because we wrote down the decimal, we can use this definition. If you don't write down what the answer is as a decimal, then you can't use this definition. All right, and we have a couple more here, so I'm just again going to go through them kind of quick. The square root of 725, again, I'm using that calculator. Second, x squared, 725, enter. And I get 26.925 and so on. So again, it equals 26.295, and it's going on forever, and it's not repeating. So by definition, this is an irrational number again. And again, using this definition of a decimal that does not stop or repeat, you can use it over and over as long as you're writing down that decimal. Number 18, 6.325, that is a decimal, right? But there's no dot, 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 so it stops. So because it stops, again, it's rational. So it's rational because it's a terminating decimal. Okay. Number 16, same thing. It's a long, long decimal, but there's no dot, dot, dot. So because there's no dot, dot, dot there to show it's going on forever, it stops. And again, by definition, rational is a terminating decimal is rational. Okay, number 19. So for me, I have to type this in the calculator, and this one's a good one to practice in the calculator. So I'm going to show you. If I do the square root of 5, so second x squared and then 5, notice how my arrow is blinking and the top bar there is kind of extending over. If you hit the arrow key, it stops the square root, where now you can type in divided by, and then you would type it in again. And you get 1. So this crazy looking thing with two irrational numbers, right? You get an answer of 1. 1 is a counting number. It's an integer, right? It's a whole number, so it's rational. So we can say it's an integer. It's a counting number. It's a whole number. You don't have to write all of these again. I'm doing it for some, and I know not others, but I'm just trying to show you. The number 0, right? That's a whole number. It's rational. Why? Whole number. That's it. Here, again, I'm typing this in my calculator to make my life easy. I'm not really sure what the answer is. So the second x squared, 10, and then the squared button is here. You just don't have to hit second, hit enter, and we get a nice number of 10. So again, 10, we can use the same definition here, right? You could just copy and paste it. Okay, it's an integer, it's a counting number, it's a whole number. So this is really the most important part of this lesson, understanding what type of numbers we're dealing with, rational or irrational. The second piece of this is operations with rational and irrational, adding them, multiplying them. What kind of answer would we get? So for this one, the sum, that means add. Right, so we're adding two rational numbers. So if I take the number 2, which is rational, and the number 4, and I add them together, I get 6, which is a rational number. So anytime, and again, I'm just showing you one example, but anytime we add two rational numbers, we will always get a rational number back. Always going to stay true. Here, the sum of two irrational numbers, that would be like me adding, because again, sum means add. If I add pi plus pi, right? Now, again, I'm going to do this in my calculator because I'm not really sure what I would get. So the pi is in blue right here. And anything in blue, we have to hit second to access. So if I hit second, and then this little caret, plus, again, second, and then the caret, I would get 6.283185301, which is a decimal that does not stop and it does not repeat, which would make it irrational. So I get 6.283, and it goes on forever, which would make it irrational. So anytime, and again, I know I'm only showing you one example, but anytime I add two irrational numbers, I'm going to get an irrational answer. Okay, and we're going to try this again with the sum of a rational number and an irrational number. So again, sum means add. If I take the number 2 and I add pi, I'm just picking easy irrational numbers. 2 is rational, pi is irrational. And if I add them together and I do 2 plus pi, I get 5.141, and it goes on forever. Right? It doesn't repeat. So in this case, because it doesn't stop and it doesn't repeat, I'm always going to get an irrational answer. Okay, so for these are always true. Two rational numbers, when we add them, we get a rational answer. Two irrational numbers, when we add them, we get an irrational number. And whenever I take a rational and an irrational and add them, I get an irrational number. And again, try it. So anytime maybe a question might ask you to do this, try them, see what kind of numbers you get, and then figure out from there what they are. Okay, so this is the big one that we kind of have to focus on, that you have to kind of remember. This is the one that always pops up on tests, on, exams, whatever it might be. So we're going to highlight this one. Oh, not working. My bad. Here we go. We want to highlight this because this is the most important, and you'll hear me keep saying it, statement, because this statement in particular can be proven two ways. So with this statement, and I'm going to kind of draw a squiggly down it because we're going to show it two different ways. Product means multiply. So if I multiply pi times pi, okay, I'm going to get, and I'm going to show you, second caret times second caret. I get an irrational answer. I get 9.8696, right? And it goes on forever. This is giving me an irrational answer. But let's just say I take the square root of 6, which is irrational. So if I took the square root of 6 and I put in my calculator, I can see that that's an irrational number. And let's just say I multiplied it by itself, the square root of 6. So let's try it. The square root of 6, remember to hit the arrow key to get out, times the square root of 6. I get a whole number. So a whole number, guys, is rational. So what I just did was I proved this statement two different ways. So this particular statement that I have starred, that I have highlighted, right? It's not always true. I can't say that when I take the product of two irrational numbers, I'm always going to get irrational answers. I can't say that. This statement, for some reason, it's just a reoccurring statement that always pops up on tests, on any exams that we see. It's always there. The rest of these kind of hold true to what they are. So the product, again, means we're going to multiply of two rational numbers. So 2 times 4, right, is 8. I'm always going to get a rational answer. Always. Here, the product of a rational, and we're just going to add non-zero because zero kind of changes it all. So if I take a non-zero rational number like 2, and I multiply it by an irrational number, let's say pi. Okay, again, if I do this in my calculator, 2 times pi, I get 6.2831 ... which is a number that goes on forever and doesn't stop or repeat, which means it's irrational. So I know that this was just a real lot of information that I just threw at you. Again, this is something that I would actually do in class with you, which is why I went so fast through it. But it's good to have it on video, so now you guys can go back and look at it. Again, this is the statement right here that I want you guys to make sure you understand. You can prove it 2 different ways. So right here, practice problems, and I'm going to, again, go through these. Which statement is not always true? This is exactly what I was saying. They're always going to kind of go back to. It's not always true. What is false? Right? So it's that statement that talks about the product of 2 irrational numbers. So you're always going to jet to that example. The product of 2 irrational numbers is irrational. That's false. So that's the one that's not true. I can also state that it would be rational, right? We proved that up top. Okay. Here, this is a good one to practice. It's basically saying I'm giving you 4 things and what they're equal to. This is what they're equal to. And I want to know which one is going to give me a rational number, right? So remember, a rational number is a terminating decimal. It's a repeating decimal. It's a whole number. It's a counting number. It's an integer. It's a nice number. So what you would do here is try them. L plus M. Well, L is the square root of 2. Plus M, which is 3 square root of 3, right? Put that in your calculator and try it. See what kind of number you get. M, which again is 3 square root of 3, plus N, which is the square root of 16. Again, put it in your calculator. What kind of number do you get? The next one, N plus P. N, we just did, is the square root of 16 plus P, which is the square root of 9. Okay, and the last one, same thing, the square root of 9, which is P, plus L, which is the square root of 2. So I'm just going to try number 3. Obviously, I know what the answer is. You guys could try this at home on your own. If I did the square root of 16, arrowed out, and did plus the square root of 9, I would get 7. 7 is my rational number. It's my rational answer here. So this would be the answer choice that I'd be looking for. Okay, again, you would try these all at home and see what you get. You could pause the video and try them. Okay, number 3, Ms. Fox asked her class, what is the sum? So again, we just talked about this. Sum means add of 4.2 and the square root of 2, rational or irrational. Patrick's answered and said that the sum would be irrational. We want to state if he's right, and we want to justify or explain why. So how would I figure this out? I would have to put this in my calculator. So 4.2 plus the square root of 2. And we get 5.6142 ... So again, this is a decimal that goes on forever, right? Doesn't stop, doesn't repeat. So is Patrick right that it's irrational? Yeah, Patrick is right. So we're going to say Patrick is correct. You're going to say the answer or the sum you could say, does not stop or repeat, right? So you always want to make sure you can justify, and I kind of talked about that in class. You always want to be able to explain. Okay, so number 4 says, is the sum of 3 square root of 2 and 4 square root of 2 rational or irrational? And explain your answer. So again, it's asking you to do the exact same thing. Take the sum, which means add, of 3 square root of 2 and 4 square root of 2, and tell me if it's rational or irrational. So again, we're going to go back to our calculators, and we're just going to try them. So 3 square root of 2, and again, the arrow is blinking, so make sure you hit that, plus 4 square root of 2, and hit enter. And we get 9.89949 ... Right? So this is an irrational answer. And why is it irrational? We can say because irrational, because we have to explain. It's a decimal. That does not stop or repeat. Okay. If it's hard to read my handwriting, remember I always have the copy of class notes posted, so you can just look on there. Number 5 is multiple choice. Jessica is asked if 3 pi is a rational number. What's the most logical response? Well, as soon as we see that number or symbol pi, pi is always irrational, not rational. So the first thing we're going to eliminate here is anything that says that it's rational, because it's not. So choice B says it's rational, which is so untrue, and so does D. It's not rational, it's irrational. Now we have to look at the reason why. Why is this number irrational? Well, we kind of said that pi makes it irrational. So you're looking for the answer choice that says that. A says no, it is irrational because any multiple of pi is irrational. Well, talks about pi, and we'll just read C to make sure or rule it out. It says no, it's irrational because 3 is a prime number. So that has nothing to do, or no reasoning as to why it would be irrational. So C is out. Okay, and number 6 is just a little practice with placing the numbers on the number line. So it's just a matter of converting and using your calculator. So if you were to take the square root of 5, we have to make all these numbers look the same. So we do the square root again of 5. And we're going to write it as a decimal. So we get 2.236. And I'm just going to make it go on forever. 3 over 2, again, we can divide that. 3 divided by 2, we get 1.5. Negative 0.5 is already a decimal. Here, if I put this in the calculator, it would be negative square root of 4, enter, which is negative 2. And then if we do pi, it's 3.14. So what we want to do now is create this number line where we can actually edit or put these answers or numbers on it. So if we put 0 in the middle, we have 1, 2, 3. We have -1, -2, and -3. Okay, so what we're going to do now is just kind of put these numbers on there. So we have the first one, the square root of 5 is 2.2. So that's going to be like right around here. And when you add it in, you always want to go back and use the original number, which was the square root of 5. The next one we have is 1.5, which would be in the middle of 1 and 2. And again, we want to use the original, which is 3 over 2. Negative 0.5 is going to be in between 0 and -1, which would be here. And -2 is going to be right on -2 here, which we want to always use the original, negative square root of 4. And then pi 3.14 is going to be about here. So again, we're just organizing this on the number line. Okay, guys, so that's the end of the lesson. If any part of it you needed to rewatch, please go back and rewatch it.